Welcome everyone to this webinar, our last event of the year. I'm Tony Roskilly. I'm Professor of Energy Systems here at Durham University, and I lead the EPSRC Network Plus in hydrogen fuel transportation. So this event is organized through that network and is part of a series of webinars looking into different aspects of hydrogen research in the transport sector. So this week we welcome two speakers on the subject of hydrogen production and supply for transportation. And our next presenter is Jorge Agueverre. He is going to give a presentation on the application of advanced model-based design of electrolyzer systems. He is a director of the Electrochemical Cells and Reactors practice within Siemens PSE Energy and Chemicals Business Unit. He has a MSc in Chemical Process Engineering from UCL. George has 8 years experience in developing advanced models of electrochemical cells and their validation and use for cell, stack, and system design and optimization in fuel cells and electrolyzers. So over to you, Jorge.
Thanks everyone for joining today, and thank you for the introduction. Just to give you a brief overview of what we'll be covering during the presentation today, I'll start by describing the principles and practice of digital design, and then describe green hydrogen production systems briefly, before moving on to how we use digital R&D to validate models, and then digital design to deploy those models to create value. And I'll finish by giving a case study of how these models are used to design and optimize green hydrogen production systems. So the model-based design lifecycle for electrochemical cells in this case, but this applies across different technologies. In electrochemical cells, this begins always with experiments. These are technologies that are being developed and changing day by day. So we find that for any given system, nothing kind of out of the box will be as predictive as it needs to be. So we typically start any activity by combining data and models, and tuning model parameters to turn that model into a digital twin. This digital twin can then start to mimic the behavior of real equipment, and we can start using that as a tool for design. So we can add some feeds under controlled conditions, and we can start to study the transit behavior. We can start to look at the profiles of temperature, composition, pressure inside the unit, and start to choose materials and design our stack. But then, no piece of equipment ever operates on its own. It always needs a system around it to support its operation. And that is key in determining the lifetime of the equipment, the efficiency. And so, within one framework, we support our customers in going from the experiment level, which can be either lab bench small cell experiments, or it can be taking experimental data from full-scale equipment, through this life cycle that ends up with optimizing a system. And we provide tools for using high-fidelity models within these systems, and give tools to analyze the global behavior of the system, as I'll describe later. So green hydrogen production, just a very quick mention. Essentially, the key characteristic of these systems is that you take renewable power, carbon-free power source, and you generate hydrogen from it. Typically, almost exclusively is done using an electrolyzer, which is an electrochemical conversion device that takes electricity and converts water into hydrogen and oxygen. The electrolyzer unit itself is quite a complicated piece of equipment. which contains flow regions for feeding reactants and collecting products. And then there's typically some backing layers for where material diffuses to what's the membrane electrode assembly, so the anode catalyst, membrane, and cathode catalyst, where the reactions take place and where there's ion migration within the cell that allows the electron flow outside the cell. And we model this equipment using multiphase dynamic models that take as much advantage as possible of first principles of chemical engineering to do mass energy, momentum, and charge balances, as well as a lot of literature information to model the electrochemistry that happens in the membrane electrode assembly. A lot of this, due to the complexity of the materials, is based on correlations that are fit to experimental data. But in a lot of cases, we constantly inputting new correlations to support customers who are dealing with new materials. In terms of how this looks when we work with our customers, we've created an interface for a model that can be configured using a dialog box, so people can input the sizing and operation of the cell, as well as there's tabs that allow users to specify the properties of the various layers that I mentioned are present, and they're able to configure the type of materials that make up all of this. In addition, there's inputs for what the electrochemical reactions that are taking place are. So while our focus has been so far on PEM electrolysis, there are ways to configure this model to simulate other electrolysis processes as well. But today I'll be focusing on the use of a PEM electrolyzer model. And at the basic level, simulating this can give you an overview of the performance in terms of the current, the amount of power, electric power going in, and measure of efficiency, how much power is lost in this process and how much hydrogen is produced from a given amount of power, as well as very detailed results of what is actually going on inside, which can help support design decisions. So determining how much catalyst to load can help by looking at the reaction profile in the anode catalyst layer. And it's possible to look at temperature profiles to ensure that the equipment is operating within the range that it was designed for, as well as looking at multi-phase behavior inside some of these other layers and seeing what the vapor liquid fractions are inside the equipment to ensure that there's enough water, for example, still reaching the electrode and reacting, and the vapor bubbles are not preventing the reaction from continuing. So how we achieve this is we start with a model, and the model at start has some default values for parameters. And when we compare that to data, it's often at a start quite far off. And some parameter tuning can help bring these values closer to the experimental data. But often when you're looking at performance over a wide range of temperatures, wide range of loads, pressures, things, it's very difficult to tune parameters to match all of the different operating regimes. But we do essentially have an optimizer that allows the model to select the optimal values of these parameters so that the model can start predicting really what happens. And this is a process. It's a very iterative process. You rarely ever get one bit of data, put it into the model, and have a model that's perfectly predictive. So quite often, you'll do this at different scales, put data into the model, compare again with the equipment, maybe scale it up, run the simulations again, compare with new equipment, different equipment, put more data into the model, and you start building up confidence that the model will predict what goes on in the equipment as you deploy it into wider systems. And at this stage is where you have what we call a digital process twin. And this can be used to essentially minimize the time it takes to go to market, to develop this technology and be able to take it to market with confidence, taking into account any risk that might be associated. In green hydrogen systems, we deal with very temperamental supply of energy from wind or solar power. And so, quite often, systems need to be able to cope with that. So, moving on past digital R&D, where you're validating models, a validated model on its own is not of any value. The value comes from using that model in the right way. So in the simplest possible scenario, one could explore the design space. So you could look at, how the operation of the equipment is under certain conditions. And then you could change an input and see how that affects the outputs. And you could even do this, hundreds or thousands of times to get a map of how the equipment will perform over a range over the design space, essentially. And this gives you, some idea of where to take the design to make it as efficient as possible. So far, we've focused on the electrolyzer itself, but as I said, the value in this comes really from how you use this model to look at the overall technology that you're trying to design. So in this case, we'll be looking at a system that takes renewable energy, puts it into an electrolyzer, produces hydrogen, it knocks the water out, compresses it, and sends it to storage. Supply it to a downstream process. In this case, we don't specify what that process is. We just have a constraint on what the hydrogen supply needs to be. Now, when we're looking at green hydrogen production, the first inputs that are needed are essentially the design and operation. So, cell configuration, stack configuration, cooling, compression, things like that, as well as set points for temperature, pressure. But we also need to consider the environmental inputs, things that are uncertain. We don't know what the renewable energy availability will be on a given day in the future. And we don't know where the prices will be for hydrogen or for any of the materials we use and things like that. And a third uncertainty, often overlooked, I guess, is the model uncertainty. We validated this model based on data, and we get a certain degree of confidence that the model is predicting properly. But when we tune parameters, it's important to recognize that quite often there could be an uncertainty there, and it's possible to look at these parameters that we estimated. How much do they really impact what the model is predicting? We may find that if one parameter is really impacting quite significantly the outputs, we need to go back and make sure that we have the confidence needed in that parameter. And finally, once we put all those inputs into a validated model, we can start to look at the key performance indicators of the process and start to really optimize and make decisions. So we'll start by looking at what the system configuration is that we're looking at. It starts with a feed of water into the system. That water goes into a tank and then flows into a heat exchanger before it goes into the electrolyzer. Now, from the electrolyzer, you get one stream that has oxygen and water, and that goes into the initial tank where the oxygen is separated and the water is sent back down to the heat exchanger. That water is hotter, so it needs to be cooled down. And on the other side, humid hydrogen exits, and we separate some of the water, then cool it and takes more of the water out. And finally, that goes into a compression train. In this case, we're compressing it to 450 bar. And then it goes into a storage tank, and we take some of that hydrogen as demanded by a downstream process. So in the simplest possible case, we can look at putting a certain power load into the system and looking at if we had that amount of power at steady state, how much hydrogen we'd be producing, how much hydrogen we'd be losing in the oxygen stream, as well as what our utilization of water is, system efficiency. But we can also input the power using PV panel model, where we specify the ambient conditions over time, so time series, solar radiance, ambient temperature, wind velocity, and we model the solar panels themselves to calculate what the power supply will be for that given period of time. And as before, we can look at the performances of the system, but in this case, not on a steady state, but as it varies over time, and we can start to track different things like how much power is going into the compressors compared to what we're using to produce hydrogen, check the safety limits of hydrogen leakage into the oxygen stream, and look at our controller performance and the ability to maintain the set points that we've specified across the system. And looking at the hydrogen storage and starting to track how that pressure is fluctuating over time, making sure that essentially during downtimes in power availability, our hydrogen buffers don't go below the limits we want them to, or similarly, that we never have to start curtailing energy because we don't have enough storage for hydrogen. And finally, we can set up global system analysis activities where we start to look at running, in this case, 1600 simulations, looking at a lot of different model predictions for different power availability profiles, different operating set points. And once that is executed, this can be executed using multiple processors. It can be deployed to HPC machines, but essentially what we get in the end is, in this case, 1600 simulations of different different weather profiles and how the system performs under them, and we can start to see what our expected efficiency is, what our expected production is as an average over that time. And we can look at the current density that the cell has been operated at over all of these, and start to kind of zoom into individual days and see we can check what the voltage of the cell is doing. But we can also start to look at contour maps where we look at, okay, what's the average renewable energy availability in these scenarios, and what power am I operating at, and what's the hydrogen production. In this case, you can see that in some cases, increasing the amount of power that you want to use in the system doesn't necessarily improve the hydrogen you deliver downstream, because sometimes that power is not available. So you can start to track how much you push your system and how much that increases the likelihood that you'll have downtime in the hydrogen supply to your downstream process. So in this case, the blue area are no downtime, systems operating as it should. As we move to the right and we start pushing the system more, we see that there's a much higher risk of there being supply downtime. And depending on what we're supplying this hydrogen to, this may or may not be a big deal. So if you're supplying this to an ammonia reactor, you would definitely not want downtime in that supply, because then you'll have to deal with starting up and shutting down reactors. On the other hand, if this is going to a fueling station where there is another storage that can act as a buffer, then perhaps you have limits on supply downtime that are a bit more relaxed. So in summary, why do people want to use model-based design? First reason is that it reduced the amount of experimentation that's needed, and it reduced the design iterations and prototypes or pilot plants that need to be built. And as you build knowledge into these models, that they kind of become a central single source of truth for process knowledge that can be used time and time again to either deploy the technology again and again, or to start to work on next generation technologies. And with these process models, the models we have are not limited to electrolyzer systems. So this can be extended to include further and further parts of the process. And ultimately, being able to do these simulations at a very large scale can help to quantify risk and make very well-informed decisions, as well as once the process is up and running, the models can be deployed to real-time applications to monitor and optimize the process as it progresses through the process life cycle. Once the equipment has degraded to a degree, a new optimization could be run to find what the optimal set points are for that particular time in the equipment's lifetime. So with that, I'll thank you for joining today, and I'll pass this back so that we can start the Q&A.